I just wanted to go through a couple NRA things. Again, the schedule for research pays off. We'll be highlighting a number of different projects next month on December 17th. Tom Burnham from the Minnesota Department of Transportation is going to be presenting on the MIRA equipment that's been used for concrete investigations, and he'll be highlighting some of his work in Wisconsin that he went over and did through NRA. Then January 21st, we'll have our next one, and February, and so on and so forth. Highlighting in January, TRB committee, NRA presence there. Lauren had that in the newsletter details. But again, the goals there for TRB is for the NRA members to promote the NRA and the partnership. We'll have a booth there. We'll also have a meeting on Wednesday night from 6:30 to 8. The idea there is to bring other states there. So the goal is to kind of expand our membership and to get other states that might be interested or just might want to be interested to hear what's going on. And when you talk about what's going on, I pulled together some information the other day, but it's pretty impressive what we've all done together combined. You know, we have eight states, Illinois Tollway, working together. We have over 55 associate members. We've funded over $4.4 million of projects, efforts going on. We have 37 projects funded so far. Again, that's short-term, long-term research, but a wide range of pavement research that's, you know, something that each state wants to kind of work on together on a regional, national basis. You look at the funding, you know, it is expensive, I guess, when you talk about NRA in a way. It's $150,000 a year for states that are larger than Minnesota. But just for Minnesota itself, the money that we've put in, we've paid 15% of that 4.4 million. So we're getting quite a benefit already, about 85% return just on our research dollars that way. So that's good news. You know, it's really helped us retain quality staff here at Minroad. And also we've gained a lot more regional and national exposure in the use of Minroad on a national facility. So with that, I just wanted to share a little bit on some of the really kind of exciting details on NRA. Related to today, again, everyone please mute your computer, your phone lines, computer. Bora is going to be talking to us again on this subject on large aggregate bases and large stone subbases. But again, Bora is a faculty member of the Department of Civil Engineering at Michigan State University and is affiliated member with Iowa State University. He just made a move over to Michigan State. Again, his main research focus is the use of recycled materials and transportation infrastructure and sustainable geotechnical practices. So, Bora, please take it from here, and thank you for doing this today.
Yep. Thank you very much, Ben. I'm really glad to be here presenting this work, and of course we really appreciate the NRA's support on this project and all states and agency members and other members that are making this project happen. Again, like Dan said, the title of the project is Determining Pavement Design Criteria for Recycled Aggregate Base and Large Stone Subbase. This project started almost 2 years ago from now, in last November 2017. So we were able to finish more than half of the project, and we hope to finish that by next November 2020. So hopefully next November's research pays off seminar, we will provide entire portion of the results of this study. I am going to present today, but this is a team effort. Halil Ceylan, Ashley Bass, and Junjing Zhang from Iowa State University help us out with some throughout this project on specific tasks. And Tans Redil and William Lykos, Bill Lykos from University of Wisconsin-Madison help us out quite a bit on these project too. So it's a team effort, and of course our research personnel, graduate student Haluk Choban is doing an amazing job on this project. So I think some of them will be on the call today, some of them couldn't make it due to a schedule conflict. So again, we would really appreciate the Ray. and the associate members. We really appreciate their support. And today's outline is kind of give a repetitive information that we've done for all these research pays off, overall introduction, why this project is needed and what is its motivation was, and the objectives of the project overall, and talk about the research plan a little bit, and go over the test cells, 11 test cells that were built for this project to monitor it, and laboratory testing. And this research pays off talk really will be on the laboratory testing results mainly. Last time we talked about the construction data and design of the test cells, and at this research pays off we will talk about the laboratory test, which was a very big portion of the project. And then we will talk about what we have learned and some recommendations and what are the progress that we are currently working on the other tasks. So overall introduction, flexible payments or rigid payments is, especially with the especially flexible payment is one of the mostly used payment systems, and also rigid payments, it's the same. Both for flexible payments and rigid payments, really payment foundation systems are very important. The aggregate base layer qualities and sub-base layer qualities are important, especially not only stiffness wise, but also permeability wise. The quality and the capacity of these materials that are used in payment foundation systems are very important. And one of the things that why such project is needed, and what are the needs, why we can't use just virgin aggregates. The map here on the right bottom hand, kind of shaded areas are showing where the aggregate sources are low quality. As you can see, almost 50% of the US has low quality aggregate sources, virgin aggregate sources. And the glaciated Midwest, where Iowa, Minnesota, some portion of South Dakota and North Dakota and north of Missouri have these glaciated Midwest also have very low quality aggregates, and same with Colorado and the southeast part of the United States. So there are issues with the high quality, getting a high quality virgin aggregates, and there were some in the even last few decades, but we keep using these virgin aggregates from the original quarries, and that keeps, and of course it's not infinite, it's a finite sources. So we keep using these natural sources, so the amount of quality aggregate sources decreases, and that increases the demand, that increases the price of virgin aggregates. So you have higher demand and less amount of natural resources. So it increases the virgin aggregate costs quite a bit. And that also brings up to economical and environmentally friendly issues. And there are some issues sometimes with virgin aggregates in terms of long lasting issues, especially if they are not high quality virgin aggregates. And in terms of alternative materials in this project, how about we recycle some of the concrete aggregates and REP materials, recycled asphalt pavement materials, and some large stone aggregates to use as a sub-base and base material to see how they will perform in the actual field conditions, and by using laboratory tests, try to predict their performance for future designs. In this study, there are two main recycled materials that we used. The recycled concrete aggregate, I will refer it as RCA from now on, and recycled asphalt pavement, I will refer it as a RAP from now on. And then large stone sub-bases. The reason why these large stone sub-bases are important, it provides good drainage. It's expected to provide good drainage, and its crushing operation is much energy efficient and cost efficient for quarries, and that decreases the energy consumption, and along with that it will decrease its process price. So it was interesting to use these three different type of materials with different combinations and check to see how they perform. So research motivation, really one of the main issue with use of these RCA and REP materials are their variety and uncertainty. And at the end of the project, one of the main things really come up with a design specification that, hey, if I want to use RCA material, how much absorption value or what should be the gradation of the RCA or rep material that I use, what should be the asphalt binder content, mortar content limit, so I can comfortably use, what should be the compaction degree of these materials when I apply it to the field. And there are limitations for the large stone subbase, there are limitations of how to characterize these materials, and can I use some other image analysis method to determine the gradation of these materials. And then at the end, by compiling all this data, can I, in addition to the design specs, can I also come up with some prediction of engineering properties from index properties by the gravel to sand ratio, the effective particle diameter values, or fines content, or angularity values of these materials. And these were the three main objectives of this study. So far, last time again, we talked about the FWD, LWD, DCP, and intelligent compaction data on the construction side, constructed test sections before it had any vehicle load on it. And today I will mainly talk about the index and engineering properties, unsaturated, saturated behavior of these materials. And in the second goal, we try to develop a method to estimate the stiffness and permeability. We are still working on this goal, but we're almost done with this goal too. And we try to relate the stiffness values, laboratory stiffness values at the first phase to and permeability to percent crushing of these particles after compaction, and their sphericity and angularity and other gradation characteristics. And the third goal will be to come up with this pavement design specifications and try to do some brief life cycle cost analysis to check to see if the application that we do is really in long term provide some good benefit in terms of life cycle. And we have test sections built thanks to Minrad on the Minrad road facility on the low volume road test section. It is a 2-lane closed loop. Inside lane is where the traffic is simulated, and outside lane is where the monitoring sensors and all are installed. And we are running the continuously Minrad is sharing the continuously run FWD, surface deflection values, and the frost event tau weakening data with us, along with the other environmental sensors such as water content, metric suction potentials, and temperature data. So with our next two tests, which I won't talk here, we are going to relate these sensor data to these FWD and surface deflection values to get to see how these materials perform after at least 2 freezing and thaw seasons. And just a brief overall information about our test sections on Minrad facility. So we have 4 different aggregate, recycled aggregate bases. First of all, each test sections have 3.5 inches superwave asphalt layer. Then we have recycled aggregate base sections with 12-inch thick coarse RCA and 12-inch thick fine RCA and 12-inch thick limestone virgin aggregate and 12-inch thick RCA and rep test sections. Then beneath them we have 3.5 inches select granular bottom material, and then cells, coarse RCA and fine RCA have sand subgrade, and limestone and RCA rep material have clay loam subgrade. Then we have a total of 7 large stone subbases. 2 of the large stone subbases have 6-inch thick class 6 aggregates and 18-inch thick large stone subbase materials, which I referred as LSSB from now on top of a clay loam subgrade. The reason why we have 2 identical large stone subbase, the idea was to build one of the large stones 18-inch thick large stone subbase in 2 layers. However, the constructability and use of these materials are challenging, so such lift application couldn't be done because compaction couldn't be done on the first lift properly. And then we had 5 different test sections with large stone subbases, and the first 4 large stone subbase test sections here built below with class 5Q aggregate layers, 6-inch thick, and then 9-inch thick large stone subbases, and one of them built with triaxial geogrid on top of clay loam subgrade, and this section here built with the combination of geotextile and geogrid and then another one built with biaxial geogrid with geotextile, and then this section built with biaxial geogrid, and one section built with 9-inch thick large stone subbase with no geotextile. The reason why geotextiles and geogrids were used, there were rutting issues on the subgrade once large stone subbase were put. So these geosynthetic materials were used to eliminate that clay subgrade to infiltrate on the pump into the large stone subbase at the bottom, which may cause drainage issues, and then also provide some additional stiffness and strength, load bearing capacity to these test sections. And these are the pictures of the subgrade soils and the RCA materials and the base materials along with the large stone subbase materials that we have collected. One thing that I want to point out, and the data will show too, class 6 aggregate and class 5Q aggregates, as you can see from the picture, even though they are not virgin materials and even though they are not called as RCA and RCA rep, we realize that especially with class 5Q aggregate, it smells like cement. So it smells like exactly how coarse RCA were smelling. So it was interesting to see that mortar content values will show that class 5Q aggregate has good large amount of RCAs in it. And if you look at the class 6 aggregates picture, as you can see, it is even darker than RCA rep mixtures. And our results show that class 6 aggregate had both RCA and quite a bit rep materials embedded in it. So it was interesting observations. And even with some of the coarse RCA and fine RCA had some sort of rep materials in them. And we have conducted the grain size distribution of all of these materials, and I have the grain size distribution graph on the right and the summary of the major characteristics of these gradations on in the table on the left. And of course, coarse RCA had the highest gravel content and limestone, and the class 5Q aggregate had quite a bit good gravel content. One thing that we focus on the AASHTO classification, of course, sand subgrade and clay loam had a little bit lower quality, and clay loam is A6, and sand subgrade A1B, and select granular barrow material is A1B, and all other materials in terms of gradation except limestone were classified as A1A, which is a good gradation that you want to have when you're building your base layers. And we have conducted specific gravity and absorption tests for all materials, and we look into the both calculated 3 of them: oven dry specific gravity, saturated surface dry specific gravity, and apparent specific gravity, along with the absorption values. And in geomaterials analysis, when you use for pavement foundation geomaterials and subgrade and base layer materials, we usually use the oven dry specific gravity. And one thing that we observed, really, the RCA materials or materials that has RCA and rep in it tend to have lower specific gravity values. As you can see, limestone, large stone subbase, and select granular barrow material, clay loam, and subgrade had relatively higher specific gravities compared to RCA and RCA rep and class 6, class 5Q aggregate materials. This was caused because of the low specific gravity of the mortar content and the asphalt binders compared to natural materials. And another thing that we focused on absorption values. This absorption value, we plan to use this for once we complete this study for the design specifications, but we need to confirm it with field data. There may be some limit to define whether this material is RCA or not based on absorption values. If you look at the materials that I mentioned, coarse RCA, fine RCA, and class 5Q aggregate along with the RCA rep, tend to have much higher absorption values compared to the rest of the other materials. And even class 6 aggregate has some RCA, so its absorption value is very high compared to natural virgin aggregates and natural soils that are used. And we have conducted a modified Proctor test, and this is a kind of graph that shows the moisture content, like moisture content dry density relationship of these materials. And as expected, limestone and the natural soils, sandy, except clay loam, sandy subgrade, and the select granular bottom material with the two replicates to ensure their results, that they have the lowest optimum moisture content and highest dry density. Then we look at the other RCA and rep mixed soils, the moisture content of these materials were relatively higher, optimum moisture content were relatively higher than the virgin materials, and lower maximum dry densities. Of course, I'm not counting the clay loam subgrade on these comparisons. So, and then we have conducted asphalt binder, try to determine the asphalt binder content of these materials, and figure we have used two methods, ignition method and quantitative extraction method. In the ignition method, you put it in an oven and apply a very high temperature to burn basically all those asphalt binders and to suck the air out of the oven. And this method provides a relative values, provide values that tell us relatively RCA rep had the highest binder content compared to other materials. But however, with this ignition method, the temperature is too high, you also burn some of the other lightweight minerals in these soils that are not really asphalt binders. And then also due to vacuum, some of these lightweight materials are sucked up in the vacuum system, and that cause a weight loss. So we also did the quantitative extraction, chemical extraction method, which is more precise. You're using the chemicals to extract these binders from your materials. And as you can see, values between the ignition method and quantitative extraction method decrease significantly. And when we look at this, of course, RCA rep and class 5, class 6 aggregate had the highest asphalt binder in any cases with any method. So methods were very consistent with each other in terms of results. And as you can see, coarse RCA even had some sort of rep particles, and as you can see from the picture here, we determined some rep particles went into this. And then we will talk about how this asphalt binder content can be used to determine whether this material should be called as rep embedded material or not based on these asphalt binder content values. And residual mortar content determination of the materials were very important. And we use kind of soundness test application, but apply in addition to that freezing and thawing cycles to ensure that we get rid of as much as residual mortars stick on the materials or residual mortars that are stick themselves as an aggregate shape. And as you can see, coarse RCA and fine RCA had the highest residual mortar content. And then class 5Q aggregate had the highest residual mortar content. If you remember that I was talking to the picture of these test sections, and class 5Q aggregate was smelling like cement when we opened the bucket. So we are not surprised to see this much high residual mortar content. And RCA rep and class 6 aggregate had quite a bit residual mortar content too, when limestone really didn't have significant mortar content. And then one of the tasks to determine the water repellency of these materials. And we have conducted two tests, apparent contact angle and water drop penetration time. And basically what you do, you drop a TI water on top of each particles, and we selected 25 particles from each, representative 25 particles from each batch. And we did this analysis only for the specimens that are retained on number 4C, coarse aggregate materials. And as you can see, the RCA materials and limestone and class 5Q aggregate, which has high RCA in it, were very hydrophilic. The water drop penetration time was less than 5 minutes, and if you can look at the pictures, when you drop the water, it's absorbed on the surface of the RCA, limestone, and class 5Q aggregates right away, so we couldn't get a picture of it. On the other hand, if you look at the RCA rep and class 6 aggregate particles, we drop the water on it, and that droplet sits there for a long period of time, especially for RCA rep and class 6 aggregate. It stayed there more than 3,600 seconds, indicating that they are highly hydrophobic. Same with the apparent contact angle. And if your apparent contact angle is higher than 0 degrees, that means your soil has some hydrophobicity. But if it is close to 90 degrees, that means it's very strongly hydrophobic material. The reason why we measure this water repellency may be useful to relate to permeability of these materials, which I will talk about in the next few slides. Thanks to University of Wisconsin-Madison's facilities, we were able to run all these three different type of tests, two different type of tests: constant head permeability test and the falling head permeability test. And these are the pictures of the test systems. And one thing that I will go quickly, that this figure shows the hydraulic conductive permeability values of each materials that we have collected and each materials that we have compacted at different degree of compaction. So degree of compaction values we've used, we compact the materials in 90%, 95%, and 100% degree of compaction. And as expected, clay loam had the lowest hydraulic conductivity on the y-axis. I have the saturated hydraulic conductivity values with their corresponding dry compaction density values. And of course, subgrade clay soil had the lowest hydraulic conductivity, and it is the most affected by the degree of compaction as expected in terms of hydraulic conductivity values. Then we look at the other materials. The impact of degree of compaction were kind of similar to each of the materials. However, with the coarse RCA, we saw a lower hydraulic conductivity than the fine RCA materials, which was surprising. The reason for this, a little bit on the test methodology that we used. We see for all these tests we had to see for per method, we have to see the materials through 3/4 of an inch materials, and that kind of allow us this. That changed the gradation of the coarse RCA and increases fines content by percentage when we are running the test. But the other main thing that affect this permeability with the coarse RCA, especially with degree of compaction, when you compact the coarse RCAs in particular, those coarse particles broke it apart much at a higher rate. Same with the class 5Q aggregates. And that also, of course, increases the fines content in the soil and causes a decrease in the hydraulic conductivity permeability of these values. So in the last few sections, one recommendation that we have, RCA materials are significantly impacted by the compaction, and maybe instead of reaching to 95% or 100% degree of compaction for permeability's sake, we may have to compact it at 90%, which is a discussion that we will have with the tech further along the way once we finalize other continuing field test data for this project too. One of the other great contributions of this study was the soil water characteristic curve analysis. And this is a figure on the right, shows the suction on the y-axis and volumetric water content values on the x-axis. And you have the initial drying curve and the wetting curve here. And in the geomaterials application, we deal with this initial drying curve, which is easy to get for our purposes. And we are able to get this data with three measurements: hanging column test, which can be used for coarse materials that can apply suction up to 6 psi, and pressure plate test that can go suction up to 220 psi. An activity meter test basically it doesn't necessarily apply suction, but it measures, you have very small particle materials that you apply suction over 220 psi, and it measures the relative humidity and convert that relative humidity to the suction values. And we get this laboratory data fit in the Van Gennington model, and this is the equation that we use. So we have these dot values obtained from the test, volumetric water content versus suction values, and then we fit this data to this solid line to Van Gennington model to check to see if our data makes sense, whether we made a mistake in the method or method is not the accurate method to use. So we use the hanging column test for the sand subgrade, class 6 aggregates, and some of the class 5Q aggregates with no problem. As you can see, the data fits fairly well with the Van Gennington model. But however, with some of the class 5Q aggregates and fine RCA material here on the right, our data point doesn't fit to this Van Gennington model when we use a hanging column test. And the reason for that, the suction 6 psi maximum suction that we apply does not really help to get the right data. As you can see, especially with RCAs and class 5Q aggregate, cementation of RCA occurs, so that becomes an issue. So we switch to pressure plate and activity meter test for RCA materials. And as you can see, this is the Van Gennington model, and the test data that you get, the pressure plate data that you can get is almost 1,000 kPa and almost 10,000 psi. And then beyond that, you need to do the activity meter measurements to really get this full suction versus your full soil water characteristic curve. And these are the data that we have collected by basically we combine, superpose the data from pressure plate, activity meters, data for this coarse RCA, fine RCA, RCA rep, and limestone. The reason why the soil water characteristics curves are important, we're going to do it in the next few months. Metric suction has a direct impact on the stiffness of the materials. And metric suction and volumetric water content is has great correlation. So based on the volumetric water content of the sample, by using indirectly with the suction values, we should be able to predict the stiffness of these materials. The stiffness test of all these materials were conducted by Dr. Suhail, Dr. Nazarian at University of Texas at El Paso. So we are working with him to correlate these soil water characteristic curve data with the stiffness resin modulus data that he has conducted on these materials. So this part, the main portion of the soil water characteristic curve data, will help us with the design section in the further along with this project. And we also look at the impacts of degree of compaction on the air entry pressure and the soil water characteristic curve values. And as you can see, the less compaction that you apply, of course, the material can suck more water with the same amount of suction. And if you compact it higher, the volumetric water content at lower degrees will provide you the same suction value to you. So it was good to predict that and confirm it in this study too. And another thing that we did the image analysis, and this is the schematic diagram of the test setup that we have. So we use the stereophotography analysis to determine the angularity, roundness of our aggregate particles, and the gradation characteristics. And what we did, basically take the image of the particle, we lay the particles on this white paper, and we take the image on the left position and slide it to the right, and take another image on the right, and create a binary image by using one of these pictures. And then by the MATLAB code created by Dr. Zhang, who's the co-PI in the study, we created these 3D dimensions of these materials. So in the X and Y axis, you can measure the dimensions of the materials in 2D, and the red line, the colored counter plots, kind of shows the third dimension of these materials. And this is the first we look at how we can use this code to predict the large gradation of the aggregate materials, including limestone subbase and other aggregate materials. And as you can see, the sieve analysis gradation and the image of the materials align well with each other, indicating that our more code works pretty well kind of to simulate and determine the grain size distribution of these materials. And we also calculate the sphericity and roundness of these materials. In terms of sphericity, limestone subbase had less sphericity compared to other materials. But the roundness of the large subbase was much smaller, indicating that they are much more angular, as usually we can expect that too. But there wasn't much significant difference on average by the roundness and angularity of these materials that are used in this study. And another thing that we completed is the gyratory compaction and abrasion values of these materials, because it was really important to see how after compaction you make your design based on the initial gradation of these materials, and you want to know how it changes after compaction if it is keep its original gradation, to be honest. And we conduct the gyratory compaction test and apply 100, 300, and 500 gyrations to see if these aggregates are standing still, they're breaking apart or not, and also how the mortars and asphalt binders in this aggregate matrix changes after compaction. And this is the figure on the left. This shows one of the example that we did for the coarse RCA material, and figure on the left shows the gradation change before compaction all the way to the after 500 gyrations for coarse aggregate, coarse RCA material. And as you can see, the curve moves up, up. And that shows the gradation changes. And how significant that gradation, how we can quantify that. We use this figure on the right-hand side that we calculate the BT value, total breakage, and breakage potential. So BT value is the area of the area of the A, that's lightly shaded area. And then BP, breaking potential, is the lightly shaded area and darkly shaded area. And then we compare this, how after these gyratory compactions, how the breakage potential of each materials are. As you can see, the coarse RCA, which has the highest residual mortar content along with the class 5Q aggregate, had the highest breakage potential. So this is a kind of warning that even though original gradation is coarse, doesn't necessarily mean that it will keep its original gradation after compaction. And if you look at the total breakage of these materials, all of them, with RCAs, we really have significant problems. Coarse RCA, fine RCA, and again, class 5Q aggregate has total breakage. And with gyration increases, especially with core RCAs, after 500 gyrations, there is a significant increase in total breakage. And same with the class 5Q aggregate, and even with fine RCA, while other materials, they impacted, but not as significant as the RCA materials. And we look at the impact of compaction on the roundness and sphericity of these materials. There are some slight changes, but not much. So we concluded that compaction during the construction doesn't really impact the particle characteristics, surface morphology of these aggregates. So I have the slides, summary of these slides, that basically specific gravity and absorption of values of these materials are kind of related. The RCA and rep mixed materials had lower specific gravities and absorption value for fine RCA and coarse RCA and class 5Q aggregates, like materials that has residual mortar and it has higher absorption values as expected. And for the compaction characteristics, virgin materials, aggregates or natural soils had lower optimum moisture content and higher maximum dry densities. And ignition method is not preferred. We recommend DOTs or associate members to really go with the quantitative extraction to determine the binder content. And residual mortar content might be a data to be used to select what type of RCA materials or what type of aggregate base material that you want to use in the pavement foundations. And with the water repellency and permeability data, I won't go line by line here. I think I already exceed my time. We will try to correlate this water repellency to the permeability characteristics of these materials. And if you have higher rep content, it will help for the permeability of these materials. And of course, degree of compaction is very important. It higher the compaction degree, lower the permeability of these materials. And one thing with the compaction, these permeability of these materials will change significantly for RCA. So it was really important to observe this in this study. And in terms of soil water characteristic test, we are working on relating the suction values to the and volumetric water content values to the MR values, to the resident modulus values. So hopefully next research phase of the seminar in the spring, we hope to provide some information on that too. And in terms of, we have a code, in terms of image analysis, we have a code that will enable DOT to do image analysis on the gradation characterization, especially for the large stone subbase materials, so you don't need to sieve that. And the breakage potential and total breakage values show that with RCAs, extra care should be taken care because their breakage potential and total breakage are very high. However, the compaction doesn't seem to change the sphericity and roundness of these materials that significantly. And some recommendations for classification or specifications right now, and these are not certain. We are still waiting to finish the all field data analysis for the long-term, to determine the long-term performance of these test sections. I think if you use ignition or quantitative extraction values, to call that material as a rep mixed material, maybe the binder content is higher than 3% or 1.5%, and degree of compaction, especially for coarse RCA, maybe should be between 90 to 95%, really, because its gradation changes significantly at high compaction degrees. And our recommendation at the moment, at this point, then you're making the gradation characteristics of especially coarse grain RCAs or even class 5Q aggregate type of materials, maybe run a gradation test after compaction and then use that after compaction gradation for your designs. And these are some of the, again, at the moment, our things how the specs and guidelines should be updated. If the material that you use as a base layer, if its absorption value is higher than 6%, that means it has a significant residual mortar content and somewhat equivalent material, and that should be treated as RCA. And asphalt binder, if it is higher than 3 or 1.5%, is good quality to have, and it is recommended for this, maybe residual mortar content should be less than 25% for this material. So again, I acknowledge all my collaborators on this project and our researchers, Sinan Choban, on this. So thank you very much for being patient with us, and we'll be happy to answer any questions.
Bora, very nice job with your team, your work and your team's work. Open it up to any questions. If you'd unmute your line, please let us know if you have some questions or comments.
Hello.
Hello. Go ahead.
Hi, this is Ahmed Ghazi, Cetin for Winnipeg. Thanks for the work and the presentation. I just have a question regarding the decreasing the percent of the compaction. If we decrease the percent of the compaction for recycled aggregate for 90 or 95%, what's the effect in the road itself, in the profiling or in the settlement?
Great question. So it is something that we are going to answer in the next few months. Like I said, in addition, when we're trying to correlate metric suction with Dr. Nazarian at UTEP, and we will, I think he also look into these different degree of compaction on these materials. So we will have a better understanding, particularly on these materials characterization in terms of stiffness, how decreasing this degree of compaction will impact the stiffness. Of course, the stiffness and settlement issue will come into the equation. So we did some literature review on that. I don't want to make up anything now. So, but of course, the stiffness and strength will decrease and settlement may increase a little bit. But how much is it? I don't remember on top of my head, and I will have a better idea about it once we finish the analysis with UTEP data.
Okay, thank you.
Yeah.
Any other questions? Bora, I have one question. I know I visited Sweden. This has been a while, and they did their gradations after compaction. They actually did. So the contractor had to kind of understand what would happen with that, the breakage.
Mm-hmm.
Do you see a benefit of going to something like that, or would you say that there's certain materials, I think you were saying, that really don't break, so you don't have to worry about them, but there are ones that are susceptible to breakage? How would a state put that into their specification?
Great. Yeah, great question, Ben. So our initial thought at this moment to really look into the absorption values to get a quick absorption value, and that we try to correlate that absorption value to the RCA content. So I think quarries, if they also give you the absorption value of their materials, or the agencies run their own absorption test on these materials, if let's say maybe put an absorption things, if the absorption of these quarry materials are higher than 6%, that means it has high breakage potential. That means it has residual mortar content, and therefore it will have higher breakage potential. So that type of specifications can be embedded to specify this.
And I guess one of my last questions is what % do you think your project is complete in your mind, just as a rough number?
65%, 60%.
Oh man, alrighty, perfect. Thank you.
Yeah, I mean we can say 72, but I think I want to be conservative.
All right, I about get you that close. Any other questions out there from the audience? I guess anything else, Bora, you'd like to add before we sign off?
I really appreciate your guys' support as well as my collaborators' support on this, and of course Sinan Çoban, I keep bringing his name up, great PhD student who is doing majority of these lab works and data analysis and all that. So thank you very much all. It's a great group effort and great agency support too. So.
Alrighty, well thank you. Very nice presentation, and thank you for spending your time with us today. So everyone else, I hope you all have a good day, and we'll talk soon. Take care now.